Hello everyone, welcome to this workshop on cloud architectures. My name is Sébastien Farges and I am CTO at Indexima. And today I'm going to talk to you about the different trends for implementing a big data architectures in the cloud, and especially how to optimize the cost performance ratio of these architectures. First, we'll see what the different trends are in terms of big data architecture in the cloud. Then we'll compare these trends, strengths and weakness and the costs. And finally, we'll see through a live demo how to improve the cost performance ratio by integrating a big data acceleration solution. So the first architecture that we must mention is the historical approach, which is the on-premise data warehouse. Before describing this architecture, a little reminder. A data warehouse is therefore a relational database which is used to collect and store information from operational database. So it collects data from various sources in order to make analysis and allow decisions for business decisions. Classic data warehouse solutions are, for example, Oracle, Teradata, or Vertica. In this architecture, the data is perfectly structured prior to loading the data. So there is an ETL layer to extract, transform, and load the data. And the data warehouse stores this data and prepares it according to the various expected reports by constituting data marts or cubes, which pre-aggregate the data according to the indicators made available in the data visualization tools. In this standard reporting pipeline, with a large number of preparation and aggregation steps in the ETL or in the cube or data mart, we can implement an efficient reporting, which was sufficient before the big data. We'll now see what changes with big data and what are the limitations of this architecture that have led to invent new architectures. Okay, so why do we need a new architecture? The big data is here. Okay, data volumes are increasing massively, and we are just starting to measure the business value of this data and the correlations or signals it contains. And this value is, in my opinion, still largely underestimated. But on-premise data warehouse architectures have several fundamental limitations. They have performance issues. When the volume of data increases, they are not prepared to scale up in terms of performance. Your ETL load and the load to constitute cubes and data mart will increase linearly. They have scalability issues. On-premise infrastructure does not allow you to benefit from the flexibility of cloud infrastructure, and the on-premise data warehouse solutions are not designed for elasticity. And finally, there is lack of agility since the processing chain from the ETL cubes data mart must evolve with each with each change of data. The IT department is often a bottleneck. Even if big data induce increasingly volatile data, each time you want to add a dimension or extend the scope of data, you will have to ask your IT department. But apart from those issues to scale and to extend performance, there is a deeper change, a deeper paradigm in big data. Big data is not just the same thing bigger. In a big data architecture, we do not know the value of the data before having analyzed it. It's therefore no longer a question of planning and constituting a report, then deducing from it the chain of processing necessary to constitute it. It's on the contrary a question of making everything available to the analyst without making any assumptions about the value of such or such column. So the volume of data in the data warehouse is exploding not only because the operational system generate more data, but above all because we are now seeing business value in dimensions that would have been suppressed or aggregated in the past. There is therefore a need to evolve towards an agile solution with a shorter chain, allowing analysts to be as close as possible to the data. And so we want analysts to have access to a larger volume of data and to have access to all the raw data. It's the analyst that decides at the business intelligence layer in the data visualization and the data science level what information is relevant. So to meet the goal of scalability, all big data architecture have moved on to the cloud. Depending on the use cases, two trends have emerged to meet those objectives of big data. So the first trend is the cloud data warehouse. In summary, we could say that this architecture is exactly the same as the on-premise architecture, but on a much larger scale. Thanks to an excellent horizontal scalability, elasticity made possible by the separation of the storage layer and the compute layer, the actors of cloud data warehouse allow a very large volume of data to be transferred to the data warehouse. And this solution will offer analysts access to much finer and broader data. The example of a solution for a cloud data warehouse are, of course, Snowflake, BigQuery, or Redshift. So excellent scalability. But the chain remains very long. With a project load, each time you want to add a new dimension, you need to change your ETL, to change your cube or data mart. There is always a project cost to extend the scope of data. And the raw data is still hidden by ETLs and structured. So in a growing big data context, the options for managing a very large volume are either to scale the data warehouse, but with a cost that can quickly become prohibitive to maintain acceptable performance. Or the other option is to put back an aggregation phase on the server side, so put back data marts or cubes. But again, you are no longer allowing the analyst to use the finest data, and you require some project phases at each evolution of the data. The other trend that is developing is the Datalake architecture. So as a reminder, a Datalake is a distributed file system. It can be HDFS, S3, CPH, in which all the data generated by the sources are stored in flat files. And there is Datalake engine on top of the Datalake, of course, which allows you to query these files directly in SQL without any prior processing or without ingesting the data in a SQL database. In a data warehouse, the data was stored in a format linked to the relational database, in which the structure of the data is predetermined in advance. With the data lake, on the contrary, the data is stored as it was generated by the operating system, therefore with a more flexible structure. As an example, the solution of Cloud Data Lake, we can talk about Athena, Databricks, or Dremio, for example. So the Cloud Data Lake solution gives the analyst much more direct access to the source data. There is no more ETL steps limiting analysis capabilities. The analyst sees all the data and can query it. So what's the catch? Well, even if, despite the major progress in recent years, requesting a large data volume on file does not allow for agile business intelligence. Response times will quickly be in the order of a minute at best if you want to query billions of lines on a file. So here again, re-implementing a pre-aggregation phase on the server side will be essential at a point to allow the analyst to browse those data without having to wait a minute between each click. So if we compare these three architectures that we have just described, in summary, we'll have a first option with a non-premise data warehouse solution that meets the needs of business intelligence on a small volume of data, but which in a big data context will show limits on scalability and agility, with a bottleneck that remains at the on the IT department as soon as the data evolves, and an inability for the analyst to access all the raw data. Next to that, we have a cloud data warehouse solution, which will scale perfectly whatever the volume, but with a cost performance ratio that is too high for big data uses. You will have to choose a point between performance at a high cost or data reduction. A cloud data lake solution, at last, which will have excellent scalability and can be used for very various use cases due to the use of open source formats. But the performance of a data lake engine will not allow you to walk through the big data volume of datasets with acceptable response time. I mean, and finally, you will need to put back some pre-aggregation on top of your data lake to have an acceptable response time. But what we've seen is that any form of non-dynamic aggregation reduces the value of big data, since it poses hypotheses on the interest of data, and that go against the principle of big data, which is no assumption on the value of this dimension or this one. So to achieve big data promise, the cost performance ratio in any case will be very high. From those discoveries, we see that there is a need for a self-service solution, which meets the following objectives. First, shows the analyst all the raw data from all sources. This is a big data promise, I call it this way. The second is remove any IT bottleneck. Be able to add a new dimension with little or no IT intervention, and no need to rework totally an ETL or a cube data mart process. And finally, to allow the analyst to perform any query with a performance below a second, and with a cost-effective solution. So in order to align with those objectives, at Indexima, we believe that there is only one economically viable solution, which is to aggregate the data, but dynamically according to the usage of the reporting. So it's not predetermined. The aggregation is not predetermined by any projection of what should be the reporting, what would be the question of the analyst. No, we wait for the analyst to ask anything in the reporting layer, and then the aggregation is automatically built based on the question of the analyst. So I will now perform a live demonstration on a classic use case. We'll see what it actually looks like to request 12 billion lines on a cloud data warehouse. So for this demonstration, I will use a very fast cloud data warehouse. I will use a Snowflake. I loaded open source data on US air traffic into my data warehouse. So it contains all intra-US flights by airline, airports, date, departure and arrival cities, etc. The data model is a star model with a fact table of 20 billion lines and dimension tables with information on airlines, airports, localization, etc. There is absolutely no preparation of data upstream. So I built a dashboard in the Tableau visualization application in order to represent this data and analyze the average departure and arrival delays. Let me show it to you. So this is my dashboard. This dashboard is directly connected to my oops, sorry for this. So this is my dashboard. So this dashboard is directly connected to Snowflake. I'm gonna select another city. For example, there is a lot of traffic in Atlanta, I think. This is the main hub. So Tableau is sending some queries to Snowflake. Here on the dashboard, I can see the average delay by year at departure. How many flights are in my current selection? So for the moment, I was on a very small city, Aberdeen. I can see the map of those different cities. As you can see, it's quite long. Right now, I'm running on a Snowflake 3x large cluster, which is already quite a big cluster. It costs something like $400,000 per year. Okay, I got to reply in something like 45, 50 seconds. So is it slow or is it fast? Well, technically, it's very impressive because I just scanned almost 700 million lines in a data set of 20 billions in only 50 seconds. It's very, very impressive. Okay, it's very impressive, but in reality, not only do analysts dislike wasting time waiting for the data, but above all, these processing times are totally incompatible with the principle to walk through the data. With this response time of 50 seconds, you must anticipate the question before. While the very principle of big data will be to discover correlation without having made any assumption upstream. So we must therefore find a way to bring this processing time down to below 1 second in order to be able to walk through the data literally. What are our options? Well, the first option, you call your best data engineer, and normally what they will propose you in this current use case we are running on Snowflake, so there is a trivial solution. I was using a 3x large cluster. I just need a 4x large cluster. My request that was 50 seconds will go down to 25 seconds. Well, having said that, 25 seconds is still way too much for analysts. And my annual Snowflake cost will rise to $800K. So it's the cost performance ratio is not achievable. It's too expensive, and 25 seconds is still way too much for my analysts. The second option is to transform the big to small. Okay, it's crazy and economically not feasible to scan this volume of data each time you have a question. We have to transform it to a smaller volume. Okay, fine, but technically, what does it mean? It means I'm going to put back some cubes. I'm on Snowflake, so I'm gonna call it a materialized view. So my IT department will build a new chain to prepare this data and to prepare the materialized view. Okay, it will work. My dashboard will be very quick. But doing this, first, I put back IT bottleneck each time I want to change a dimension, I want to change something to my data and to the scope of my data. And most importantly, I reduced the data set that is available to my analyst, which is the opposite we want to do in big data. I took some, transforming the big to small, I did some assumption about what is the value of data and what are the questions my analyst will ask. So to sum it up, transforming the big to small is meaning time-consuming BI projects, losing in agility, and data reduced to a subset of the data. So I'm not comfortable with those options. What we propose is another solution, is to fully automate the implementation of this aggregation layer, so as to continue to expose all the data, all the fine-grained data to the analyst, but automate the aggregation. So Indexima is a big data accelerator which connects to any data source and which fully and transparently create hyper indexes, which is the way we aggregate the data. So by learning from the usage and from the query patterns, our machine learning system makes it possible to speed up requests and to optimize also the memory usage. So let's see what the addition of this accelerator can bring to our US traffic use case. So here we are above a data warehouse, but we could be on top of data lake engine also. So I will show you how in few clicks, Indexima will allow us to solve the dilemma we have on the cost performance ratio. So I will add Indexima between my Snowflake source and my Tableau dashboard. Let's see how to do it. So this is an Indexima cluster I prepared previously. This is a small cluster. It's 2 nodes on AWS. I think it's M5, 2x large, so it's few thousand, I think it's 3,000 euro per year, something like that. A very small cluster. So there is no data for the moment on this cluster, 40 giga RAM. I'm gonna create the link between Indexima and Snowflake. How to do it? You just select your source. Okay, I want to create a new schema. Where is the host? My Snowflake host, my credentials, my warehouse. Okay, let's connect. Okay, I found Indexima found my schema on Snowflake, and I create the link, and I'm done. Now I can send any request on my data to Indexima instead to send it to Snowflake. This is a query view of Indexima where you can see every query that have been sent to the Indexima cluster. Now I will do the same on my Tableau dashboard. I will swap my dashboard. I should have had this in cache, but anyhow, I will swap my my dashboard from the Snowflake source to the Indexima source. Well, he's still requesting something from Snowflake. I switch back to a smaller city. Whatever, let's cancel it. So in order to change the source, I'm gonna use I have you to cancel. Okay, so I will replace the data source. For the moment, I am on the Snowflake data source, and I will ask to go to the Indexima data source. Okay, I can see immediately that Tableau is sending some queries to Indexima. Immediately here, you see, queries are executing. Let's see how adding Indexima between Snowflake and Tableau will improve our dashboard speed. for the moment, not so much. Let's go to the flight map. Yeah, okay, I have multiple values here. Okay, so Tableau is sending some query. Okay, I can see a few queries going through here. Okay, 20 seconds. So we were somewhere between 45 and 50 seconds with a direct connection to Snowflake. Okay, almost the same, right? Well, okay, 30 seconds, not really different. Okay, let's try another city. Let's try I don't know, Baltimore. Up. Okay, oops, still very slow. Let me explain to you why it's still very slow. Let's go a little bit deeper in how Indexima works. So at the beginning, Indexima has just created a link between Indexima and Snowflake, and so Tableau is sending some queries to Indexima, but Indexima didn't generate any aggregation layer. So every queries hitting Indexima are immediately delegated to Snowflake without any manipulation. Then Indexima is listening for queries running and learning from the query patterns it sees. After learning for a while of this on the usage and on the query patterns, Indexima will start to build some hyperindexes, some aggregation of the data that would allow to quickly reply to the same kind of question. So our totally automatic process of analyzer will at one decide to generate an hyperindex. And once some hyperindexes are generated, the queries will start to be replied directly by Indexima and won't be delegated anymore to Snowflake. And finally, after a while of machine learning, Indexima will be able to reply to pretty much any queries without having to delegate anything to Snowflake. Okay, so let's see how it works on our dashboard. So I can see right here that Indexima has started to learn from the query patterns. I can see this because this is an alter table. So as you can see previously, every request, every real request, this is a dummy request from Tableau, but every real request was directly delegated to Snowflake. But this is an alter table creating an hyperindex. So Indexima decided to generate this hyperindex, which is a complex join between 1, 2, 3, 4, 5 tables, and so Indexima sent a request to Snowflake to generate this hyperindex. Okay, 3 hyperindex have been generated already, and it seems Indexima doesn't generate it more right now. So let's see the impact on our dashboard. Okay, I was in Baltimore. Let's try Austin. Okay. We were previously running with a request of 45, 50 seconds. You can see here that we have requested 90 million lines in less than 40 milliseconds. Okay, let's try a bigger city because this one was not so big. Let's try traffic in New York. Okay, we have now 400 million lines in same 40 milliseconds instead of 45 seconds. Okay, that's why last one. I think Chicago is the biggest one. Yeah, 800 million lines in same 40 milliseconds. Okay, these queries directly on Snowflake would have taken something like 50 seconds. Right now, I have some performance that really allows the analyst to go through the data without having to anticipate the question. And well, as I'm here, what about trying all the data sets? Okay, it took a little bit longer, well, a little bit longer to display for Tableau. Here it took something like 180 milliseconds and few seconds for Tableau to display it and to display so the more than 12 billion rows. So let's go back to our presentation. What we have seen right now is how we added an acceleration layer between our data warehouse and our data consumers here, or data visualization on Tableau. So in just a few clicks, we managed to go from a dashboard which took 50 seconds between each click to a dashboard which takes now 50 milliseconds between each click. But most importantly, there is no reduction of the dataset to a subset. The analyst has visibility on all the datasets, and there is no more data marts, cube effort, and the load on the ETL is really light now, because we want to send all the datasets directly available for data consumers. So if we try to sum up the values of this acceleration layer, we have seen there is a DevOps gain as we suppress some IT bottleneck by reducing the workload to create and maintain the ETL, the cubes, the data marts. So of course, as a consequence, we have gained on agility, because when we add a new dimension, we have little to no IT intervention required. We have also a financial gain, as well. I didn't say it during the demonstration, but of course, at point, your acceleration layer and Indexima will stop any queries, and your data source will have much less queries to perform. So for the demonstration, I had a Snowflake cluster 3x large with an acceleration layer. Of course, you're going to downscale this Snowflake cluster maybe to a large cluster. So a huge financial gain, because you use less compute resource on Snowflake. There is a gain on the business analyst workload because his work is accelerated. He has now less than 1 second to ask a question against 1 minute before. But most importantly, we have the big data promise that is realized, because the analyst is able to access the raw data with zero assumption. He can access everything without asking the IT department to provide a new dimension or to provide a new project for a new dashboard. So, and of course, I just gave you a demonstration on a Tableau Snowflake use case. But Indexima is compatible with many data sources and many visualization or data science tools. So if you can't see the tools you use on your architecture on this slide, don't hesitate to come and tell us about them. That's it. I'm done for this presentation of big data architecture. Thank you for your attention. If you ever want to discuss cloud architecture options in more detail, please write to us on the email here on the slide. Have a good day, everyone.